All right, welcome to the last episode of the Transformations chapter. We're looking at 3.5 inverse relations now. And let's start. All right, looking at the two lines that we've got going here. We've got the red line and the blue line. Notice again that the points on those all the way through, we are going right through that line y equals x, flipping them over, and the x and the y component, so the original x becomes the new y. Original x becomes the y. Original x becomes the y. And the original y becomes the new x. That's how we know when we have an inverse, is when the x and the y values switch. Oops. So we've got a reflection there in that line y equals x. And whenever we do a reflection in the line y equals x, we call that an inverse. And we can solve that by switching our x and the y values and then resolving for your y. For instance, let's take our original equation. They said y equals 2x plus 4. Switch the x and the y. X equals 2y plus 4. Resolve for y. Okay, subtract 4, so x minus 4 equals 2y, and now divide by 2. Y equals x minus 4 over 2. But because we're talking about lines here, let's give each of them their divide by 2. So we've got the one in front, 1/2 x minus 4 over 2 is 2. Okay, that's the other line that we had. That tells us that those two are inverse of each other, which can be written as, this is one of the ways of showing an inverse. X equals f of y. So, if we're reflecting in the line y equals x, we call that an inverse. So, reflecting line y equals x, we call that an inverse. The notation that we use, there's two of them. Let's look at the first one. Instead of saying y equals f at x, we're saying x equals f at y. Or in other words, x is a function of y. That's what that means exactly. Notice that all we did is we took the exact same equation, we switched the x and the y values. So what happens there, again, like I've been saying, is the point x comma y becomes y comma x. And following along with our replacements, our x is replaced with y, and our y is replaced with x. Let's look at the other notation that we have here for these. And that other notation is the inverse of f at x, or f inverse of x. You've seen these before. You've used this notation before. And it's not the notation that says it's an exponent of -1. That is not an exponent. Do not confuse that right now. Not an exponent. That is not saying take this function to the exponent of -1. No, it is an inverse notation that you've been using since you've learned about trigonometry. So for instance, if we had something like 0.5 equals sine of a, and we wanted to solve for that a, the only way that we can split these two is by taking this y value. That's really what we have. We have y equals sine of x, and switching our y value and our x value. And we switch those two. And if we switch those two, we use the inverse. So we would say a equals the inverse sine of 0.5. And that notation right there is the same notation that we're talking about right here. It's the inverse. Switch the x and the y. So you've actually been using it. All right, example number 1 here. Sketch the graph of the inverse, and is the inverse a function? Then the domain and range. Oh boy. Okay, so let's start with, what is a function? We got to remember that. A function, if we remember, passes the vertical line test. Every vertical line that you draw only crosses the graph once. So this original graph is a function. So a way of looking at it visually is, does it pass the vertical line test? We can also look at it and say, for every x, there is only one y. For every x value that you have, there is only one y value. That's a function. So let's start sketching. Well, first thing, let's draw in that line y equals x, because that's always going to be our reflection line. An inverse is a reflection about the line y equals x. So draw that in there. Next thing, any place that you see it cross that line or touch that line, you've got an invariant point. So invariant here, invariant there. Got to hit those lines. I'm always going to look for those ones. Then, x and y intercepts. This is an inverse. Inverses switch everything to do with x with everything to do with y. So we're going to switch all things to do with x with all things to do with y. That means x-intercepts become y-intercepts, y-intercepts become x-intercepts. Let's do that first. So we've got a y-intercept at 1. So we're going to have an x-intercept at 1. We've got a x-intercept here at like 0.5 and 1.5. So we're going to have a y-intercept at, those are negatives, so negative 0.5, negative 1.5. Let's take some of those other points that we know. Switch the x and the y values. 1, 3. That's going to be, switch it, 3, 1. Right there. And, oh, we know this point over here, negative 4 and 4. That's going to become 4 and negative 4. Switch the x and the y. And now we start connecting all of the points. Now I got one crazy point sitting here out of the way. Let's redo that garbage one. And that was supposed to be 1 and 3 and 3 and 1. There we go. That's the right stuff. Oh, we know this point here as well. That was 3, 2. So now we're 2, 3. Perfect. Okay, connect all of our points. Straight through here. Oops. Oh, yike. Let's retry that. There we go. Straight through there. Up through there. And to there. Done. This one wasn't a point that I meant to hit. Good. Looks beautiful. And it's just the same shape flipped over that line. So is the new one, is it a function? Well, let's look at our vertical line test and find out. So with the green line, we're drawing vertical lines and we're seeing, does it cross more than one place? And yeah, it does. In multiple places, it crosses more than once. Look at that. There, 3 points. It's definitely not a function. So, no, not a function. State the domain and the range of the function and its inverse. So let's look at the original. So I'll use red for the original because they drew it in red. So domain and range. Oops. Okay, there we go. So x where? Our x's start at -4 and they finish at 3. -4, 2, all the way to 3, and that's in the real number set. Beautiful. And our range starts at, look at that, -1 and goes all the way up to 4. And that's also, oops, y. And that's also YER. Love it. Now I'll use green. Let's look at the domain. Our domain starts at -1 and goes to 4. Oh, this is looking familiar. And our range starts at -4 and goes all the way up to 3. Hey, that's looking familiar as well. Huh. How interesting. I think I just said this. A function is everything to do with x becomes everything to do with y. You switch the two of them. That means everywhere originally in the original you see an x, you're going to switch that for a y. Everywhere originally you saw a y, you switch that with an x. The domain of the original is the range of the inverse. The range of the original is the domain of the inverse. So when you get a question on your exam that says, what's the range of the inverse? Don't go and draw it and then try to figure it out. Just take the domain of the original and switch the x's for y. Now you got the range of the inverse. And this page here I explained right at the beginning and all the way through. Okay. Domain of the original is the range of the inverse. Range of the original, domain of the inverse. And how do we go through and find the equation of it? Well, switch your x and your y, and work her through, and resolve for y. All right, ready for number 2 now. All right, let's take finding the inverse equation. Start with your equation. And step number 1, switch your x and your y. X equals -y squared plus 4. Resolve for the y. Subtract 4. X minus 4 equals -y squared. Multiply over the negative. So we've got -x plus 4 equals y squared. Square root both sides. Don't forget, plus and minus square root, -x plus 4, or 4 minus x, however you want to write it. Sketch the 2. Well, that first one was a quadratic, and hey, we know it's opening down, it's a quadratic parabola, opening down, and we've got a transformation here 4 units up. So we know it's going to look like that. Hey, if we're going to do our inverse, we put in our y equals x. And I'm going to be looking for certain points. Points I'm going to be looking for. Any invariant points. And I'm also going to be looking for your intercepts. 4 that's going to become a x-intercept of 4. Okay. Kind of like that. Looks more like this right here. Let's bring the real graph in so you can really see. Okay. I went way too high up here. Okay. The original was our red, and our new one is the blue. So now, is that a function, that new one, that green or the blue in theirs? And if we do that vertical line test, no, wait, it's not. It does not pass the vertical line test. There's more than one y value for every x value, so it is not a function. And having some fun with this whole concept, notice that if we take two quadratics here, and they're inverses of each other, every single point is the same distance away from that line y equals x as the other point, that corresponding point. So what it's showing there is, if you find the midpoint of those two, like the point and its inverse, you're always going to get the midpoint being y equals x every time. The midpoint falls on the reflection line. Just going through this part here quickly, we can always find the midpoint between any 2 points. They're showing here. One way of doing it is by making first of all making a triangle, right? Triangle, making that line the hypotenuse, and then finding the midpoint of the vertical, and we'll also find the midpoint of the horizontal, and look at where those two intersect each other. And if we look at where the two lines intersect, right there is going to be our midpoint, and we can then see that those coordinates 4, 3 are where the midpoint is. That's doing it graphically. We can also look at it and do it algebraically. And really, when we're doing it algebraically between 2 points, the midpoint is really the average between the two. So just go ahead and find the average x value, add the 2 x's, and divide by the 2 of them. There gives you your average of 4. And your y coordinate, add the 2 of them, divide by 2. Find the average. So 4, 3, hey, found it a different way. And that's using our midpoint formula here. The x's, add the 2 of them up, divide by 2. Average. Add the y's, divide by 2. Find the average. So your book there shows you how to find the midpoint between the two of them. And if you notice, those points are equidistant from the midpoint. And the midpoint, if you're going to find the midpoint of the two, these two numbers have to be the same. The line y equals x, that's the whole purpose of what we're doing here, is we're proving that any point along here, if we find the average, the midpoint between the two of them, it lies on the line y equals x, where the y value is equal to the x value. Everywhere on that line, the x and y coordinates are the same. Now looking at this original one, the red line, and the inverse, which is this blue line, we notice that this is not a function. But we're going to be looking at how could we change this and restrict our domain so that the inverse is a function. That's where we need to be able to go with this now. Determine 2 ways to restrict the domain of the original so that the inverse is also a function. Well, let's look at what we got here. Well, let's draw it. We got it right here. That point is 1, 3, so it's going to be 3, 1. Y-intercept the 4, x-intercept the 4, and we got something that looks kind of like that. Not perfect, but I'll go with it. That's a reflection again in our line y equals x. Well, that's not an inverse. Or sorry, that's not a function. The inverse is not a function, does not pass the vertical line test. So the only way that we can do this is if we do one of two things. First of all, we either need to take just the top portion of our graph and forget about the bottom, or just take the bottom portion of the graph and forget about the top. Well, the only way we can get to just half of the graph is if we start with only half of the graph. So if I only start with this first green side, and I reflect only that, I'm going to get the green side here, the top portion. But if I reflect the left side, I'm going to get the bottom side. So that's what we're going to do. We're going to chop this baby in half and talk about either the right side or the left side, but not both sides. That's how we can restrict the domain in two different ways. Talk about either the right or the left side. And we need to get an equation of it. So let's get the equation of the inverse. Subtract the 3. Oops. Switch the x and y first. X equals y minus 1 squared plus 3. Subtract the 3. X minus 3 equals y minus 1 squared. Square root both sides. When you take the square root, you got the plus and minus. Minus 3 equals y minus 1. This plus or minus, that's what gives us the top and the bottom side of this graph. That plus or minus is what we want to break into the positive side and the negative side of the equations. And then add up the 1 over. And I could either put it in front or behind. Doesn't really matter where you put it. This time I'll put it behind. Equals y. And I'll show you a prettier graph because mine doesn't look that great. I'll show you their nice looking stuff. So there's the first one. We are going to restrict the domain of the original so that we're either talking about just the right side, which is x greater than or equal to the 1 value, or taking the left side, which is x less than or equal to that 1 value, and the 1 was our vertex. And we've got the two different sides of the square root, either the positive or the negative square root. And you can see the result is just one side of that parabola when it's flipped over. And now we've got a function. Yay. And last one, let's just algebraically determine if these are inverses. So take one of them and try to solve for the other one. So y equals 3x minus 6. Add the 6, switch the x and y first, sorry. And 3y minus 6. Add the 6, x plus 6 equals 3y. And divide by 3, y equals x plus 6 over 3. And is that the same thing? No, it is not. We've got a plus, we got a minus. No go on that one. And let's try the other one. Y equals negative x squared plus 3. Switch the x and the y. X equals negative y squared plus 3. And subtract the 3 over. X minus 3 equals negative y squared. That looks like double equal sign, but it's not. And square root, oh no, divide by negative 1 there. So then we've got negative x plus 3 equals y squared. Square root both sides. And we got negative x plus 3 equals y. Now, I don't have to put plus and minus here because they told me something. They told me that the original domain was restricted. X was greater than or equal to 0. So I'm only taking the right side of the original. So I'm only going to take the positive side of my square root. And yes, sirree, buttons. That is the same. Because we've got square root. Ooh, they just tried to trick you up. They put the 3 in front. 3 minus x. Ooh, yay. Now, graphically, doing these. The way that you can prove this graphically is by putting in your first equation, y1, putting in your second equation, y2. So graph the first one, y1, graph the second one, y2. Also graph for yourself y3, which is y equals x. Graph that third one as well. All of them have to intersect at y equals x, so all three of them have to intersect at the same point. And you've got to notice that these will be the exact same shape, just flips over top of this third line. Same thing over here. Graph the first one as y1, graph the second one as y2, and also graph y equals x. Make sure that they all three intersect at the exact same spot, and that they're flips of each other. You'll notice that the first one, that does not happen. The second one, it does. So you can verify it graphically. And there's your 3 discuss the ideas, and you are done, finally. Whew! All right. Have fun. Oh, you're still here? Well then, without further ado, let's do some more flipping. We've been flipping this whole lesson. Let's check out some other flips. Hope you enjoy.